Welcome back, students, with the third segment of the second lecture on the course of Introduction to Category Theory. So we were there with the first lemma, and there were three statements in the first lemma. I left the first two statements as an exercise for the viewers. So for the third statement, I need to prove it. So the proof goes as follows. So there are, okay, so if, so we are given information that A is isomorphic to B and B is isomorphic to C. So since A and B are isomorphic to each other, there exists an isomorphism, and we know that isomorphism with F. Okay. And F prime is the isomorphism between B and C, and F is the isomorphism between A and B. Okay? We know from the definition of isomorphism that there exists an inverse of this function, which we will denote by G and there exists an inverse of this isomorphism F prime that we will denote by G prime from C to D, such that F composed with G is equal to the identity function on B and G composed with F is the identity function on A. Also, F prime composed with G prime is the identity function on C, and G prime composed with F prime is the identity function on B. Okay? So we have written down all these things using the hypothesis of the lemma and the definition of isomorphism. Okay. Now, we need to establish an isomorphism between A and C. Okay? Then we'll be done with the proof. Now, the following calculations will show that F prime composed with F prime composed with F is a map from the set A to C is the required isomorphism actually, which the inverse of which is given by G composed with G prime. One can easily see that G composed with G prime starts at C and ends at A. So this is what we want to prove. We want to prove that the inverse of this isomorphism is precisely this map. So let us try to do it. Compose with G, compose with G prime by invoking the associativity. We can first take the composition of F and G, put it in a bracket, and then compose the resulting functions in the given order. Equal to, what is F composed with G? Is the identity function on B. F prime composed with the identity function on B composed with G prime. Then we do this. When we perform this composition by using the property of the identity function, we immediately see that the composition of these two maps is precisely G prime. And the composition of F prime with G prime is the identity map on C. Now, what if we take them in the opposite order? We see immediately that, again invoking associativity, what is G prime composed with F prime is identity map on having function on B composed with F. Then we perform this composition first to get the function itself. And what is G composed with F? It's identity map on A. So what did we get? We got we proved that we have a function. We proved that, let me change the marker. We proved that there is a function F prime composed with F from A to C, for which there exists another function I will change the marker again. There exists another function G composed with G prime from C to A such that F prime composed with F, meaning that this function composed with this function G composed with G prime is precisely equal to the identity map on C. On the second part, we proved that the composition in the opposite order results in the identity map on A. In other words, G circle G prime composed with F prime circle F is equal to identity map on A, establishing an isomorphism between these two sets A and C, where the inverse of this map F prime circle F is precisely G circle G prime. Okay, so far so good. So we have proved the third part of the lemma. Now we move on to the discussion. Before we move on to the discussion of the cardinality of finite sets, there were a few exercises that I wanted you to do. Let me write down the exercises. You can consider them as HW. Exercise 2.1.2.12 and exercise 2.1.2.13 from page 18 of textbook. Okay? All right. Now, cardinality of finite sets. So, during one of the exercises, I showed you a clever way of dealing with the problem by taking the number of sets, of the number of elements in the given set. So basically the cardinality of a set is given by the number of elements in that set. But we need a formal definition of this cardinality of set in terms of isomorphism, which I will be giving you now. Let A be a set. Let A be a set, and the small n is any natural number. We say that A has cardinality n denoted by so we place the set A between vertical bars, and that is equal to n. This is how we denote the cardinality of the given set A. If there exists an isomorphism, if there exists an isomorphism of sets A and underbar n. What does it mean by underbar n? Let me explain. As has been stressed in the exercise of HW that I have given you a while ago, n bar denotes the finite set 1, 2, 3 all the way up to n. Example, 5 underbar means the finite set with 5 elements. The first 5 natural numbers. So n underbar n means the set of first n natural numbers. Okay. Now, once you establish this isomorphism, you conclude that the cardinality of A is precisely N. Okay. Now, if it happens to be the case that there exists some n in the set of natural numbers such that A has cardinality n, then we say that the set A is finite. That A is finite. Otherwise, we say that if it is not the case, then we say that otherwise we say that A is infinite. A is infinite, and write the cardinality of A being greater than or equal to infinity. I suggest another exercise at this stage. You consider that as an HW. .1.2.15 on page 18 of the textbook. Same page. Okay, now another lemma. I will try to state the lemma first, and I don't know if time allows me, I'll go over the proof. How much time am I left with? How many minutes? Okay, 13 more minutes to go. So let me state the lemma first. Let A and B be two sets. If there is an isomorphism of sets, if there is an isomorphism of sets, F is the given isomorphism between these two sets. You can also write it this way if you want. Then the two sets have the same cardinality. A very important result. Then the two sets have the same cardinality. Then the two sets have the same cardinality. Okay. One writes it as the cardinality of A is the same as the cardinality of B. Okay, so the stage of the proof. So how do we do the proof? Okay. We are given an isomorphism. F from A to B is a given isomorphism. Suppose the cardinality of A and B are given by the natural numbers m and n respectively, meaning that cardinality of A is m and the cardinality of B, we're making things simple by taking finite sets. Okay. So these are given. We are given the cardinality of A and B, which are also finite sets, we assume, and assume that the isomorphism between A and B are also given by F. Now, since the cardinality of set A is precisely M, by the definition of cardinality, we know that there exists an isomorphism. I have written down the definition of cardinality a few minutes ago. There exists an isomorphism A from underbar M to A. Underbar M means the set of the first M natural numbers. Okay? And also, since the cardinality of B is given by the natural number n, there exists an isomorphism B from underbar n to the set B, where underbar n means the finite set of first n natural numbers. Okay. Now, using the second statement of lemma 1, using the second statement of lemma 1, we see that B is also isomorphic to underbar n. Since underbar n is isomorphic to B, B is also isomorphic to underbar n by the second statement of lemma 1. Statement of lemma 1 B is isomorphic to underbar n via the inverse of this map. Okay. Now we have a sequence of isomorphisms. Observe the sequence of, there is a sequence of isomorphism. Isomorphisms given by this, where this is the map A, this is the given isomorphism F, and this is the map the inverse. Okay. Now, using the third statement of lemma 1, we see that since these are all isomorphisms, we see that by number 3 statement of lemma 1, this composition of map will yield the isomorphism between these two sets. And this is an isomorphism by the third statement. Now I give you the last exercise for today's class. One can prove this is an exercise for you. this is an exercise for you to prove that M is isomorphic to N is equivalent to the statement that M is equal to N. I leave it as an exercise. It's a very important result. So, okay. So, since you are done proving that M is equal to N, it implies that the cardinality of A is precisely equal to the cardinality of B. Okay. So now I tell you a few words about commutative diagrams before the end of today's lecture. We'll not discuss the commutativity of diagrams in detail because it's out of the scope in the sense that we don't have appropriate abstract algebra background, but I give you a flavor of what commutative diagram is and what we need to know for our purpose. Okay, so I write down the things in terms of pictures. So say that we have this picture. We have this picture of 3 sets and 3 functions. Okay. So there are 3 sets here, A, B, and C, and 3 functions, F, G, and H, in the prescribed directions. Okay, meaning that F is a function from the set A to B, G is a function from the set B to C, and H is a function from the set A to C. So if F, G, and H are functions, and A, B, and C are sets, we call this picture a diagram. Okay? And we say that, so this is the diagram as long as F, G, and H are functions and A, B, and C are sets. And we say that this diagram commutes if the composition of G with F is equal to H. Okay? And if this is the case, then we say that this is a commutative triangle of sets. Okay? We know what it means by the composition of 2 functions. The composition of these 2 functions should be equal to the function of function H, meaning that you can go from A to C in these 2 paths. If the 2 paths give you the same functions, then you say that the underlying diagram is a commutative diagram. Okay, another example of a commutative diagram, we consider the following picture with 4 sets and 4 functions. F, G, H, and I. Each of these assignments, F, H, G, and I are functions. They have to satisfy all the properties of functions. And each of these things, A, B, C, and D, are sets. As long as they are sets and the given arrows are functions, we call this picture a diagram. Okay? And well, we can go from A to D into different paths via this path or via this path. Okay? This way or that way. Okay? So this diagram is called commutative if G composed with F is the same as I composed with H. I composed with H. Okay? So in that case, we say that this is the commutative square of sets. Alright? Alright. So these are the preliminaries of a commutative diagram. So in this lecture, what did we do? We discussed the constituent, the main features of the category set, where the objects of this category are sets, and the morphisms of this category are functions between these object sets. So we discussed various definitions and terminologies related to these objects and morphisms of this very important category. What else did we do? We at the end of the lecture, we discussed what it means by a commutative diagram. So we will employ all these machineries to understand various other aspects of this important category called products, co-products, pullbacks, push-outs, and various other things. There is another important thing about this set of lectures given by David I. Spivak is that he introduces this notion of O-logs to somehow capture the concept of categories in the language of knowledge formation and these conceptual applications of what he calls artificial intelligences and all that. So we'll use this notion of O-logs in the next lecture. Okay. So this ends the second lecture of this online series of lectures on Introduction to Category Theory. So I thank you very much for viewing this lecture. Let us meet next week for the third lecture on Introduction to Category Theory.